today what we're going to talk about is models in which we estimate the B matrix. And you're going to learn a few examples of that. And then I'm going to go through some of the ways that, at the end, I'm going to go through some of the ways that these models are used to study community interactions. And a lot of that work has been done with the very long data set on plankton communities in Lake Washington. And I'll talk a little bit about that work. And then at the end, when we get into the lab, closer to the lab time, into this lecture, Mark and Eric will talk about their more recent work on estimating the B matrix and the way they have done that and some of the statistical issues associated with that, particularly in a Bayesian context. Okay, let's go here. All right, so this lecture is going to be divided into two parts. I'll talk about a couple different multivariate lag-P models. And in those types of, so that's a model where you don't just have x at t minus 1 affecting x at t, you also might have x at t minus 2 or x at t minus 3. I'm going to show you examples of those because those can be written as a MARSS model with lag 1. And then I'll talk about modeling community species interactions, so predator-prey interactions and competitive interactions, and talk about these two examples here with moose and wolf, and then that the other one on the other side is a fairly small plankton community food web diagram. So before I launch into talking about these models, so let's think about what happens when we add a B matrix that's not identity. So we've been fitting a lot of MARSS models in different ways. And we have been, generally speaking, treating the hidden process as a random walk. So we might have a stochastic trend, or like in the dynamic factor analysis, we have these hidden trends, and these are random walks. And in that case, the B term is a 1, so you don't have a parameter in front of the xt minus 1. And if it's a multivariate case, that B matrix is an identity matrix. So that's diagonal. It's got 1s on the diagonal and 0 everywhere else. When you were fitting the models for your homework, you didn't have to specify that because that's the default behavior. But now we're going to start estimating that B matrix, and we're not going to set it equal to a identity matrix with 1s on the diagonal. And the behavior of these models is quite different than a random walk. And this often will trip people up when they use these models. And it'll trip people up because they are trying to fit these models to data that don't look like that at all. So here is some plots of mean reversion. So mean reversion means that you have a time series that keeps being pulled back to some mean level. And in this case, I don't have anything in the model that would cause a trend. It's just a really simple, in this case, it's an AR1 model. So it's just x at time t equals some beta. In the top left, you can see what the beta was set to. That beta times x at t minus 1 plus some error. That's it. Let's see. In this particular simulation, the u term, so that b x at t minus 1 plus u, you could have a u in there. In this particular graph, that was set to 0, but it could be set to something else. And that doesn't cause a trend like upward or downward like you would see in a random walk with drift. That doesn't do that in a mean reversion model where you got that b term. All that happens is that your mean level is changing. So all I had to do was look at these graphs and see that the mean level was 0. So I knew that this was simulated with a u equals 0. So this is really important to kind of really fix this in your head, that once you start estimating that B matrix, that drift term is not causing a trend up or down. It's not like a random walk. It's fluctuating about a level, unless you put in some covariate that makes a trend. So like you could have a covariate that would be time, and then you could include a linear trend. But unless you do that, it's going to look like these graphs. Okay, so that's one thing to really keep in mind about mean reversion. And then the other thing that to kind of think about is that the size of that B, so this is the term on the diagonal of the B matrix, that gives you a sense of how tightly your data are going to fluctuate around that level. So sort of how tightly they're pulled back to that level. So in this case, B equals 0.6, that's small. Small is anything that's close to 0. And in that case, you can see it's kind of pulled tightly close to that level. And then here, the same variance, so the same process variance, but the B is closer to 1, so closer to a random walk. And you can see it's not really pulled as strongly back to the level. Okay, so we're going to start off with a multivariate AR2 model. What would that look like? So this is what it looks like, and you'll see why I have the little prime on the X here. So I've got my X, and this is multivariate, so there's multiple X's. And a multivariate autoregressive 2 model looks like this. You got your X at time t, the multivariate, and then B matrix, which let's say that this X is it's 2. Okay, so we had 2 time series there. So then the B is going to be a 2 by 2 matrix. And then this is going to be 2 rows, 1 column, time t minus 1. And then this is what makes it a lag 2. You have your beta, your second beta for the X at time t minus 1. And then you can have a U in there, and you have your errors in there. So that would be a multivariate lag 2 autoregressive model. So how do we fit this? Well, a common way that people will fit this type of model, and in fact, lag P models in general, is to rewrite it as a MARSS 1 model. So the kind of model you've been working with all through the course, a multivariate autoregressive state-space lag 1 model. And the reason for that is that a lag P model can be hard to estimate, but they're great algorithms for fitting MARSS models. And the early in the class, I mentioned the Coleman filter, and that is a really fast algorithm for fitting for estimating the underlying state estimate, so the expected value of the states. If you know the parameters, the Coleman filter, it'll just run right through it. And then the other nice thing about that is it's a very quick way to get you the likelihood. So any kind of method, any kind of fitting method that's going to use likelihood, and So that's, your maximum likelihood, obviously, your Bayesian methods. You got this really fast algorithm. So, so it can be really helpful to rewrite this as a MARS-1 model. So what does that look like? So what you have to do is you redefine what your x's mean. So now, instead of just having x at time t, my x is going to be the x at time t and the x at time t minus 1. So I've redefined my x to be these. And so if each one of these, there were 2 of them, so now I've got 4. Got x, the first one and the second one at time t, and then the first one and the second one at time t minus 1. And then all I have to do is kind of sit down on a piece of paper a little bit and think about what the new B matrix needs to look like. And so hopefully you can kind of see how this works out. If I make that B matrix, I put B1 here, so that's a 2x2 matrix there, and here's a 2x2 matrix here. And now you can see when I do that matrix multiplication, I get this equation right here, which is what I wanted. So just multiplying that. And then what I need to do is I need to have this one down here to be x at t minus 1. So what I do is I put an identity matrix here, a 2x2 identity matrix. I don't need the t minus 2, so I put a 0 there. Now I've got to work out what I do with my u. So now I'm going to have my u up here. So that's going to be 2u, 1 column, and then zeros, 2 zeros. And then I have my errors like that. And then I need to specify what my error distribution looks like. So I'm going to have my WT up here, and then I have zeros, because here this isn't a stochastic equation here. I just need to keep track of putting the xt minus 1 in the right place down there. So I don't want any error added. So I'm going to have a q up here, and then I have 0 down there. So that's the trick of how you can write that multivariate autoregressive lag 2 as a state space model. Well, I haven't showed you the observation part. So this is the process part of the MARS model, but that's the hard part, is rewriting it like that. And this kind of rewriting models like this and sort of like thinking about, oh, okay, where do those parameters go, and reformulating your B. This kind of thing is you do this all the time when you're working with multivariate data, all the time. If you look at our whiteboards, they're just full of things like this. So then we have to do our observations. Our observations are just of this one. So we have to think about how do we redo the Z matrix. And so what we want to do is we want to kind of zero that out. So our Z will have identity here. In my example, it is 2x2. So this would be a 2x2 identity matrix. And then we have our zeros. And what about our errors? Well, there are none, because we're rewriting that as a state space, and that doesn't have any observation errors in it. But that's okay. We can just say our R matrix is 0. That's fine. So let's see a little example. I'm going to do a univariate example, just so it'll be a little easier to see. So here's our, the other nice thing about doing a univariate example is I can then show you what it would look like fit with ARIMA, which will fit univariate examples. Okay, so let's just do this model. So you can see that's an AR lag 2. This is our beta 1, and that's our beta 2. So I'm just going to simulate some data using ARIMA sim. So there's my R. I'm not going to be using that. I got my B1 and my B2, same as that. And then I'm going to set Q equals 1, just like I set it here. And then So I pass in B1 and 2 as my list for AR, and then I set the Q by passing in the standard deviation as the square root of that. Okay, so sim AR2 is my simulated AR2 data, and I simulated 50 time steps. So now we need to write that AR2 as a multivariate autoregressive state space. So remember, we're going to stack our xt minus 1. Now our b is going to be the b1, b2, and then the 1 here. So now you can see when you do that matrix multiplication, we get xt is b1 times xt minus 1, b2, xt minus 2. Then we have our u, and we have our error. And then this bottom one is just tracking so that we can get our xt minus 1 over there. So we just need a 1 here. Everything else is 0. What do our errors look like? We're going to have our q there, and then this is going to be 0. What does our observation look like? It's just an observation of this. So that's our data. And then we have our z is going to be 1. So we have now recreated that equation there as a MARSS model, and we can fit that. So all we have to do, so this is how you would fit it with the MARSS package. You go through, you just carefully set up all the matrices. If you're using some other package, it's, you know, same idea. They would have a different way of specifying these matrices, but it's exactly the same idea. So we just specify what all these are. Boop, 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 boop. We make our model list. You've all have done this in the homework quite a few times. And then we pass in our data. So there's one thing that's different here, I should point out. And that is what the initial condition for the x's are. And this is actually the case whenever you are fitting models where you've set the observation error variance to 0, you can't estimate the initial value, because if the observation error variance is 0, then the x is going to be completely specified by your data in some way. In this case, it's specified by your data in a very simple way, because this is a very simple model. I'm hesitating here because we sometimes use these models where we're setting r equal to 0, and the z doesn't look so nice like that. It's something complex, and then we have to really be up there at the whiteboard trying to figure out how we specify our initial conditions. Sometimes it'll be too hard, and we're like, oh, I can't figure it out. Okay, fine, let's just add a little bit of error there to our data, which actually perversely can make it simpler. But in any case, in this case, it's really simple. And so all we have to do is recognize that we want so we need to specify the initial values here. So from our data that we're going to pass in, we can set this one into time step 1, and that one into time step 2, and then pass in the data starting at 3. So that's the trick we can use since we have r equal to 0. So where is it? Yeah, okay. So here I'm setting x equal to mu, and you can see I've set it to the second and first one, and the order is switched that way because I need to have time step 2 on the top and time step 1 on the bottom, right? So that's got to be t and t minus 1. All right, so that's what's going on there, and then that's the only tricky part. Pass that in, and I can compare what the estimates are to the truth, and you can see it does just fine. It's pretty close. as usual, I can throw in a whole bunch of missing values and things should be just fine. In this case, I've made half the data missing, and I've just kind of randomly tossed those missing values in. I can, nothing changes. My model list doesn't change. The only thing that changes is I pass in this data with missing values, and you can see it. In this case, it does quite fine. All right, so I mentioned that you could fit this with just, your base functions in R, and particularly you could do the ARIMA data. So let's look at what the estimates are with the ARIMA function. So this is how you would do it, and it will be just fine with missing data too. So let's pass in the GAPI data, and here's what you would do. You pass in order 2, and then we didn't difference our data, and we don't have no MA. We are setting the mean to 0, and you can see it comes up with the estimates just fine. And this would be much faster. So you may think, okay, why on earth would you rewrite a AR2 as a MARSS model? It's slower, and then what a mess it is to rewrite that. So you wouldn't for an AR2, but the thing is, once you get into a multivariate AR2, so you don't just have one X, you have multiple X's that you're monitoring. ARIMA is not going to work. You just can't. It's not going to work for the problem. So this is a simple example that you can fit with other better methods. But once you start getting complicated, then you're going to need to rewrite your model in this form. And then you'll have a number of ways that you can fit it, a number of packages you could use. Okay. So let's see an example of something that you couldn't fit with the ARIMA function. So this is a multivariate AR2. So imagine that you wanted to fit an AR2 model to 2 study sites where you've been collecting data. And you think that these 2 study sites are pretty similar, and that it's reasonable to assume that the B terms are the same across the sites. And what you want to do is use the information from both sites to help you estimate these. They can be kind of hard to estimate, so you'd like to maximize your data that you're bringing to bear on this problem. So this is how you could set that up, where you have these 2 independent study sites where you are monitoring. Each has one time series. So you now stack your X's. So this is study site 1, this is study site 2. And the way that you do that sharing is that you're having these parameters have the same value. So they're independent time series, but they share these parameter values. And so now when you fit this model, it's going to use all the data from both sites to help you estimate the 2 B's. And you might want to have, you could have different covariates in the sites. You could add that in there. You could also assume that maybe the process variances are different among them, so that if you actually look at the time series, it may be that one's kind of really like fluctuating like that. It has a small process variance. And so why might that be? Maybe it's kind of a sheltered site or something. And then you have another one that is really exposed to the elements, and that one fluctuates a lot. So they could look really different, and because they have different process variances, and you could allow that, but you can still use those 2 to help you estimate these 2 B terms that you think are the same across the sites. And then you have to think a little bit of what your Z matrix would look like. Here we have our site 1 and our site 2, and we just set up our Z so that we pull that X for that one, and then that set that 1 to 1 to pull that X for the second one. All right. Okay. Pause for a second. Any questions on that? Chat. Quiz time. Okay, Mark has a quiz for you guys. Is that AR2 model stationary? Oh dear, Mark, did I not include a stationary one? No, surely I did. I must have.
I think there was the univariate model back on like slide 10, or the one that you did. That one.
Not stationary? It's gotta be stationary.
Who can solve the quadratic equation? So this, we're going to drag you all the way back to like was it beginning of week 2?
I'm letting you guys answer that one.
I'm not suggesting we dwell on this. It was mostly when I saw it go by. I thought
Oh,
it was a
okay.
good check. People can submit the answer with their homework this week, and we'll give you a bonus point if you get it right.
Wait, but wouldn't it? I think ARIMA sim complains if you try to do something that's not stationary. Anyhow, okay, we can chat later about this. Okay, anyhow. Okay, I've got to find my thing here. Okay. All right. Any other questions, thoughts? We'll jump to another example of where we use the B matrix. Okay, so another common way that you would see a B matrix that is not an identity matrix is in models where you have autoregressive errors. So not MA errors, autoregressive, which are a little bit different, kind of similar, a little bit different. And so the way that you would do that one, this is kind of funny. So this is a model that I've seen a number of times, and like you're trying to detect you've got a noisy signal. So remember we worked earlier a few classes ago where we had a stochastic level. So you can imagine that you've got that stochastic level, but you want to model the errors, the observation errors, as AR1. So you don't want to treat them as white noise. So you've got this random level that's like a random walk, and then you're observing that with autoregressive errors. So let's, oops. Oh dear, did I have it? Oh no, I'm changing topics there. Okay. So in chapter 14 in the lab book, there's an example of how you do that. And the basic idea, so this is an example where you have 3 observation time series. And the tricky thing here is to set up your process model, that state model, the X model, where you're going to incorporate your autoregressive errors into that state model. So this is our random trend. That's what we're trying to estimate. That's our signal. And you can see that it's a random walk. So x equals, that's 1 there. So x equals xt minus 1 plus noise. The W here are white noise. So we've got our white noise there. So that's our random level. And then the E's are AR1. So I have B1 times E1 at t minus 1 times the W1. So you can see that's an AR1 process. And then when I set up, so then my error structure is going to look like this. So this is like I'm using a hidden trend where I've set the variance to 1. So imagine like your dynamic linear, not dynamic linear model, dynamic factor analysis. So that would be a common assumption to set that variance to 1. So I've got that dynamic level. I've got that stochastic level. I've set that variance to 1. And then these are the error terms that I'm estimating. And in chapter 14, you'll see that there are 3 different observations. And these are the errors that are going to be added on to each of the observations. So again, what you're going to have is that R matrix is going to be 0 because you're not using those errors. You're getting your errors coming in from the state process. So you can look at lab 14 that shows you an example of this, and this is trying to estimate an underlying signal using 3 different observations of that signal. All right, so now we're going to switch gears a bit and get more ecological. And we're going to talk about a way that these MAR models, multivariate autoregressive lag1 models, have been used in studies of communities. In particular, that it's been used a lot to understand the dynamics of plankton communities. So people go out to a lake and they will take samples from the lake, like on a weekly basis, and they count all the plankton and determine what group they're in, what species or what group, and then people will use these multivariate autoregressive models to analyze that data and try to understand what's happening with the community interactions. And the model that they're using is a Gomperts model. You may have heard about this before in ecology classes. This is type of density-dependent density-dependent model. And it looks just like this. So really simple, just an AR1 model. And it has this behavior. So we've already seen this. It has mean reversion. So it's a model in which the population tends to fluctuate around some level. So density dependence. So in really kind of the broadest sense, you can think about density dependence, lag1. So that means density dependence in which the dependency is only to the previous time step. It looks like this simple little equation here. So it's the population, N is a population size. So population size at time t is some function of the population size at t minus 1. And the shape of that function determines the dynamics of the system. So, you have your, Beverton-Holt, you have your Ricker, and now you have the Gomperts is another type of density-dependent models. So there's a whole bunch of different density dependent models, and how they, differ is in the shape of that function. And it'll determine the shape of that function will determine things like whether or not it has a stable or an unstable equilibrium. So as the population goes to some level, does it tend to be attracted to that level and want to stay around there? Or does it, if it's on the equilibrium, does it tend to just sort of race off and go someplace else? The shape of that will determine how fast you tend to approach an equilibrium, what that equilibrium level is, and how does this population respond to perturbations. So we go in, we change the environment that population is in. Well, the shape of this function determines what happens. So does the population tend to like really change quickly and go to a new place and then come back to equilibrium quickly, or does it kind of wander off when it is subjected to perturbations? So exponential growth, that function would be if we just said that n at time t is just n at time t minus 1 times a constant. That's exponential growth. And now we're going to make that density dependence. We're going to add in some function here. So we have our base growth rate there, and then some function of nt minus 1. And the function that Gomperts uses is this function here. And I'll just show you what that looks like. It just kind of looks like this, which is as population gets bigger, it doesn't like go down linearly. It's kind of this exponentially looking thing. So why is Gomperts popular as a base model? Kind of two things. One is that when we take the log, so we take this and then we take the log of it, we get this nice linear equation. And that surely is a big part of the motivation in using this. Another feature of the Gomperts is that you can think of it as a locally linear approximation to a lot of other types of density dependent models. So this is really easy mathematically to work with. And then we can show that as long as the population doesn't like really change a whole lot, we can use this to approximate all kinds of other density dependent functions. All right, so here's some general properties of it. So if b is less than 1 and greater than 0, it goes towards a stable equilibrium. If it's negative, but it's greater than -1, it does this 2-point cycle thing. And that is the cases we're going to be concerned about. Well, particularly we're going to be concerned about the red one, where this is less than 1. All right, so that was without any error added to it. And what does it look like when we add error? It looks like this random walk here. And this is the case where it's less than 1. And you can see, you've seen a few plots of these like that. That's that. If we set it equal to 1, then it just wanders off. It becomes a random walk. But the red line, where the b is greater than 0 and less than 1, it doesn't wander off. It just fluctuates around here. All right, so there's critical things to know about this. One is that it goes to an equilibrium. So if you've so in like your ecology classes, I'm sure you've learned about this community models in which you have, say, like a predator-prey model, and you show that it has a certain equilibrium point where the predator and the prey will tend to go towards a certain, certain numbers of the predator and numbers of the prey. So this does kind of the same thing, except that it's stochastic. And when you're working with a stochastic system, you're going to talk about the mean of the stochastic distribution and the variance of that. Okay, so that's the key thing, is that there is some distribution. We're going to talk about that in a moment. All right, so basic features of this process, which is kind of different than some other processes for multi-species models. So like the Lotka-Volterra predator-prey model, that's really different. The Gomperts model, mean reverting, so it fluctuates around a level. It's stationary, so it doesn't like blow up. It just has some, set, variance around that level. And then key thing is a point equilibrium. And this is how it's different than like a Lotka-Volterra predator-prey. So in those types of models, you get these cycles. And the Gomperts model, predator-prey models don't do that. They're just going to have a point, and it's the predator and prey are going to kind of be a cloud around that point. And that point is a density of the prey and a density of the predator. So it's going to be a cloud kind of around those densities. Okay, so this is some caveats. Just this idea that, yes, it's a simple model, but you can approximate a lot of other types of density dependence. Okay, so so this model has a long history. People have used it a lot to try to understand density dependence in real data. And so the problem with that is that whenever you have observation error, that creates something that looks like density dependence. So it's called spurious density dependence. So that's a problem. And so what people have done to deal with that are the types of models the time series models that you're learning about, which are state space models. So you add an observation error to those models. So you're just taking I'll go here. So you're just taking this right here, you're adding on your process variance, so that becomes your stochastic Gomperts, and now you're going to add in an observation process to that simple state space model that you've been working with. It is kind of difficult, and I'm going to mention this, that it's difficult because I think Mark and Eric will talk about this later, is that whenever you have observation error, it starts to be really difficult to estimate these B matrices. It's not specific to community studies. Anytime that you're going to be estimating that B matrix, the observation error is going to create problems for you. And one of the main ways that you can deal with that, if you need to estimate the B matrix, is to use replication. So you're using a multivariate observation process, which you can fit with the class of models you're learning about, these MARSS models. And the replication is helping you get your observation error estimate. And then that allows you, in turn, to get a better estimate of the B matrix. All right, so let's see some examples, just so you can kind of see how these models are used, and then the different things that people do with them. So in the MARSS user guide, there's a little, it's kind of a toy example using the wolf and moose data from Isle Royale. This is a long-term data set. Hey, oh my gosh. Oh no. I had a time series showing you that. I guess it must have fallen below somehow. Okay, so this is like, I'm going to say 40 or 50 years of data where they have the moose on an island and the wolves are on the island. And for a long time, they couldn't really get off the island. So they're just stuck there together. And the wolves are the only thing that eat the moose. And the moose are the main thing that are feeding the wolves. So it's a very nice two species system. Yes, there you go. So we can think about, okay, well, how would we model this using a MARSS model? So we would want these are our moose. Our moose have some growth rate. And then they're going to have a B term, which is the effect of moose on themselves. And then times whatever the moose wore. I didn't put the t's here. This is t minus 1. So this is moose at time t, moose at time t minus 1. And then we have a term which is the effect of the wolves on the moose times the wolves at t minus 1. And then we have a similar kind of equation for the wolves. We have the effect of the moose on the wolf and the effect of the wolves on themselves. So it looks like this, written in really compact form. Here's our moose and our wolf. And this is what is now called an interaction matrix. So this is this key thing. This captures how the moose and the wolves interact and affect each other, how they affect themselves, and then how they affect each other. Right here. And then this is the moose and the wolves in the previous time step. So you would imagine that the wolves, the effect of the wolves on the moose should be negative, and the effect, this is moose on wolf, that should be W there. The effect of moose on wolf should be positive. And in the chapter, in the user guide, it will fit exactly this model. And if you do that, what you will see that the estimates for this don't really come out as you would expect. And that highlights a key thing, is that when you're trying to estimate species interactions, it's important to include the key covariates that are driving the fluctuations of the species. And for the Isle Royale case, it's nice because they've done so much work on it. They know what are the key drivers that are affecting moose survival and affecting the wolf survival. So for the moose, it's like how deep the snow was, and then how rainy and hot it was in the summer. And in the chapter, you can include those in the model, and you will see that once you include those, you then get a B matrix that looks like what you would expect, i.e. the moose have a positive effect on the wolf and the wolves have a negative effect on the moose. All right, so that's kind of a little toy example that's in the chapter. You can just kind of look at that if you are interested in estimating species interactions. All right. Yes, I did include the time series. So this is what the time series looks like of the wolves and the moose. So the wolves also have some interesting things in that they had a epidemic. They had a disease that wiped them out. So that's what happened here. But that kind of creates an interesting perturbation. They go down, and then you see the moose going up. And I forget what happened to the moose here. It may have been like a really bad winter or something. All right, so let's use another example, and this is the example from Lake Washington. So this is a much more complex example, and here is a food web showing, or in a cartoon version, showing the interactions between a subset of the lake species, and then below, one of the key covariates that was used in the model. So this is really complex, and we want to, so it's complex, but we can write that mathematically in a really simple way, just using that multivariate autoregressive model. We have our X, we have our B, and that B matrix is capturing all of that. All right. So there are two really big things that people do with these models. One is they try to understand the stability of community systems. That's one thing. And then the second thing they'll do is they use them to try to understand the important links in the system. So, you know, you look at that, it's like, oh man, what a bunch of spaghetti, right? How do we pick out which are the ones, which of those interactions that are really driving the fluctuations in the system? We could do pairwise experiments, but these species are not existing in a pairwise environment. They're all interacting together. And this model framework can help you reduce that matrix, that big interaction, to show you which interactions are really driving the fluctuations of the system. Okay, so this is what the model looks like. So this is now going to be however many plankton species that we have. I think that was, if I recall, it's 13. This is going to be, let's say we have 13 species there. So this is, the B is going to be 13 by 13, so pretty big. We're going to demean the data, so we're going to get out the mean so that we can set that to 0. And then this is going to be whatever covariates that we include. So it's very compact, and this model is quite easy to fit. In one of the chapters in the MARSS user guide, actually, it goes through analyzing very similar data, some plankton data, shows you how to do it. Okay, so let's go back to that B matrix. So these are the self interactions, so a species on itself, and the off diagonals are the interactions between species. As I said, there have been many, many studies of this. Lots of studies of what's going on in lake plankton systems. Mark and I, oh, actually, Eric was on that too. So the three of us were involved in a big review of these studies. So if you're interested in this, you can go to this paper and see lots and lots of studies. And if you go to the site, you know, the people who are citing that, people have since used these models to look at interactions in other types of systems, non-plankton systems, and they'll also use these methods in looking at different types of interactions, not just community interactions, but other types of interactions. Okay, so yeah. Okay, got through that. Okay, so with the Lake Washington data, if you're not familiar with what was going on back in the 60s, they used to dump sewage into the lake, and you can imagine it was absolutely disgusting. And then there was a lot of community effort to get the sewage diverted. And then Tommy Edmondson led a study after the diversion in collecting these data. So we have this very long, fantastically rich data set of how the plankton were changing after the sewage was diverted out of Lake Washington. And okay. So this is what that model looks like. All the species, kind of gone over that already. We have our covariates. They look like this. We're just adding our different covariates in there. You've seen this before. Our X's are the species abundances that we're observing. And the B, the matrix, is those interaction matrices, and the C are the covariates effects. Okay, I'm not going to go into that. Okay. Extensions of this will be to include observation error. And then there have also been a number of recent studies where people look at time varying interactions. And I think Mark and Eric might talk about that because they've done a bunch of work on modeling time varying B matrices. Doing basically, remember we were studying the dynamic linear models where you have your dynamically varying like intercepts and effects of the covariates. Well, you can do something similar with your B matrix and have that be a random walk. You can also extend it, your observation matrix, and put that Z here and allow to have multiple observations of communities. So that can help you estimate your B matrix. And again, I think Mark and Eric might talk about that because they've done some recent work on that. You can have replicate study sites. That really helps you get your estimate that B matrix. Okay, so that's basically a whirlwind tour of that class of models, and I want to talk about some interesting things that you can do once you have that B matrix. And although I'm talking about this in the context of community interactions, this is generally what I'm going to be talking about are generally features of this B matrix. So you might use that B matrix for some other types of interactions. So think of like chemical interactions, say. And that's the example that comes to mind. But there are other systems where you would have interacting chemicals or species or populations, and that B matrix would capture those interactions. And everything I'm going to talk about now is going to apply to those other cases too. Okay, so let's talk about stability of interacting systems. So what does that mean? How, and by I say, what does that mean? So now we're going to talk about like, how can we talk about the idea of stability mathematically, what it means. So remember a little while ago, I talked about that those time series, they have a distribution. So we think about, we've now got our interacting species, and this, let's say plankton. So we've got all our different plankton species, and they're interacting, and this is a mean reverting system. So we know that they are fluctuating about whatever the equilibrium is, and that kind of cloud has some features. It has a mean, and it has a mean vector now. Each of the species has a mean, and it has a variance covariance matrix. So it's going to be, if we've got, 13 species, it's going to be a 13 by 13. And that describes that cloud of how the species interact, or how the species densities vary through time. It's not just sort of random, and it's not unknowable in this mathematical model. It has a really specific distribution that we can specify. And the key thing to note here is that that interaction matrix is a big part of that. The work I'm summarizing very quickly today is in this classic paper about estimating community stability. And I'm just highlighting a few things from that paper. So how can we think about the stability of that kind of cloud of, of densities, their species densities. So I'm thinking about that. I've got some time series, and my fingers here are each of my time series, and they're all moving through time. And I'm describing the different densities that they will traverse through time. And how do I describe the stability of how those things are fluctuating? There's a lot of different ways I could. 2 or 3 ways I'm going to talk about today are, 1, the return rate. So this is the idea that if I perturb that system, so we have a big storm, everything gets cold and a lot of species get killed off. So that's a perturbation. How long does it take until the system returns to equilibriums? How fast does it return? So that's one measure of stability. Reactivity would be if this environment that it's in it keeps perturbing it, how far away from the equilibrium does the system go? But what is this? Is it kind of like, does it kind of resist moving away, or does it, just sort of like, whoa, hey, I got perturbed, I'm just going to head off to a completely different place, really different species density. So that would be high reactivity. And then variance is kind of going to capture both of those. So here's the graphical image of return rates. So if you think about your system as kind of metaphorically like a bowl, and our system has an equilibrium down here, and the return rate is if we perturb it away, how fast does it come back down? So this system is more stable than this system. And this one, the sides of the bowl are not as steep. And as we perturb it away, it comes back down slowly. In these systems, that B matrix is what determines how fast you return to the equilibrium. And it's just the dominant eigenvalue of the B matrix. So the maximum eigenvalue. So if you're working in R and you fit your model to a bunch of species, a time series, a bunch of species, you got your B matrix out of there, just do the eigen and you take the maximum, you're good. Okay, reactivity. So reactivity is this idea that you perturb it, how far away does it go? So this one, again, it's not how fast it comes back, it's how far it runs off. And this is, a cartoon again, getting that idea. Reactivity is harder to estimate, harder to compute, but the key thing is it's just a function, of the B and the Q. And again, this is just highlighting the importance of that B matrix and how that can capture the sort of what's going on in this complex system. And then the last common one that's used is something called a variance comparison. And it's basically combining both the return rate and the reactivity. That's sort of how I think about it. And again, it's a function of your B and your Q. These are the 3 that I have seen commonly. And I think actually the one that I see the most commonly is just the return rate, I would say. But we'll see what Mark and Eric, what their view on that is. A recent study that was done with the Lake Washington data by Tessa Francis was looking at how the stability of the system has changed over time. So, they turned off the sewage, The system has changed, and that can change how species are interacting. So here's what was going on from 1982 to 1992, a real big shift in Daphnia. So they're much more common. And if you look at like the amount of phosphates and clarity of the water, that's what's changing here. So your big change in what the environmental drivers are. And you can estimate that B matrix for different windows of time and look at changes in the stability. So this is a measure of the maximum eigenvalue. So that is the measure of the return rate. And you can see that what it looks like is that the system has become more, let's see, return rate, the rate of return. So hopefully I don't get this wrong, Mark. I think the rate of return is higher here, so it's more stable here and less stable here. So it has become less stable, I think is the point there. So that, getting that kind of stability of the system, that's really hard to get just by looking at the time series. And the reason is, or one reason, is that when you look at time series coming out of a system that is buffeted a lot by the environment can look very unstable because the environment's throwing it around. And then another one, it may be like it doesn't fluctuate at all, but it may be looking like that because the system, the environment is very stable. It doesn't change a lot. And getting the B matrix is a way of kind of peeling back the hood and seeing like what the underlying dynamics are if they were both in a system equally buffeted by the environment. And I see that Mark has put a link to a kind of a deep dive in stability properties from MAR models. He's got a PDF there. I'll link that on the course website too if you want to dive into that later. Okay, so the last example thing that I want to talk about, that the ways that you can use this is, I mentioned in the beginning, it can help you figure out what the important interactions are. So you start out with a cartoon like this. It's got all the linkages in there, and what you want to know is, well, which of them can I like treat as zero, like effectively treat as if they don't, the two species don't interact. So I would like to be able to draw it like this and say, hey, these dark lines, these are the ones that are really important. These are the key ones that are driving what we see in the community changes. And so the way or one approach people have done for that is they start with a B matrix that has all the interactions, and they're trying to find one where they have set some interactions to zero. And basically, this is a strategy where you're searching model spaces. So this, if you look at this and the number of ways that you can put in zeros, it's a very, very large number when you calculate out all the different combinations. So you need a strategy by which you're going to compare different models. So different models are going to be models where the zeros appear in different places. And there's a lot of different strategies that people use. Exhaustive search probably wouldn't be practical if you've got a lot of species. It would not be practical if you had a lot of species. So there are various different algorithms that are used. Mark has worked on this quite a bit. Then you have your forward step models. You start out with no off diagonal terms, no interactions. You're adding them. You can do a backwards strategy. You start with the full model and start removing things. So there's different strategies that you might use. All right, and so that, yeah, okay. So in the user guide, as I said, it walks through repeating the analysis that you'll see in the Ives et al. 2003 paper. They very nicely shared their data, and we have that data in the MARSS package. And so you can go through and basically redo their analysis, very close to their analysis. It's a little bit different. All right, and yeah, so I'm going to stop there.
So I will jump through this pretty quick just to cut to the chase. There's Eric and there's our colleague Steve. So as I mentioned, this is not a new problem, right? I mean, from a statistical sense, people have been trying to do this for kind of 25 years now, probably more so. But ecologists have been obsessed with this for probably 100 years and trying to figure these things out. And, you know, I have close personal experiences with having worked a little bit with Bob Payne and certainly spent hours arguing with him about the way the world worked. But Bob was really fascinated in these things as well. And he spent a lot of time trying to figure out interaction strengths between things like Piesaster and mussels and barnacles. And he was able to do work in a very tractable experimental system, right? He could go out there, pull all these sea stars off of rocks, put copper rings around things and exclude them. As an undergraduate, I had the great fortune of working with Steve Carpenter from the University of Wisconsin. Worked on this lake he's standing in front of quite a bit. I spent 3 summers of my life there every week. And Steve was also someone who's really interested in these kind of topics. So, you know, the idea is that, well, if you've got some time series, this is basically what Eli was talking about today, can you estimate interaction strengths among these things from this? So I'm going to skip through this because this is what Eli was just talking about. So we've got packages out there that exist to do this work. And there's also, as I'm mentioning, other ways to do this. And Eric and I, Steve, have been playing around with doing this in most recently STAN. And this is really our driving question here. How accurate and precise are these models when it comes to sort of uncovering these things? Because people are sort of running around now willy-nilly just doing this all over the place and believing that the answers they get are real. So what we did was simulated a really simple food chain. This is not even a food web. Okay, so there's 4 members. Each one of them is operating under density dependence at some varying level. Each one of them is a prey. Well, I shouldn't say that. 3 of them are prey, 3 of them are predators. And then we impose different levels of sampling or observation error and then different levels of process error. And the idea was, could we recover, right? When we knew the truth, could we get that out? And so we did this in STAN, and then we started messing around with prior information, because if you think about this, the arrows that I've drawn here in this food chain, in a lot of cases, people know something about this from like experimental studies or that type of work. It's not just, you know, that we necessarily operate in a vacuum. So we thought, well, let's just pretend we know something about this and we can start to make some more informed decisions. So basically, to cut to the chase here, you all know Bayes' rules. Eric talked about this before, right? So if you know something about your prior information, the data tell you something about the likelihood, the combination gives you that. So this is a graphical representation of that B matrix that Eli was just talking about. The upper right and lower left corners, they're just zeroed out. It was just for easy plotting purposes. So you can ignore those 6 boxes that don't look like there's any results in there. So this down the diagonal is the strength of the density dependence, if you will. And then these are the top-down effects up here, and these on the subdiagonal are the bottom-up effects. And when environmental noise, so this is the process variation, is much greater than the sampling error, it doesn't even have to be a lot greater, But so when Mother Nature is throwing the system around much more than your ability to observe what's going on, we actually do a pretty good job of recovering these. And what's on the x-axis here, the difference between those three box and whisker plots, is it's the amount of prior information that we place on those parameters. So it's 10% error, 50%, or 100% is basically what you're looking at. And so that's really affecting the precision a lot here, more so than the accuracy. You know, there's a few cases where maybe that's not doing well, but in general, this is doing pretty well. And so from an accuracy standpoint, we're pretty happy about this. And precision, this is sort of natural. This is what you'd expect. If you knew more about it, then you'd be more precise. However, in the situation which is much more common in ecology and environmental science, the sampling variance often is much larger than the environmental variance, depending on which animals you're talking about. And this result was rather shocking. You see along the diagonal here, that when we tell the system that we know pretty sure what this is, or this value is, we can recover it. But as soon as our prior information becomes much more diffuse, we routinely underestimate what's going on here. And we've also done some additional things where, let's say now we had 2 or 3 surveys and we piled those up on top of here. In this previous situation, the precision will shrink a lot because that will even help us better understand what's going on. But in this case, adding more and more observations doesn't really gain you much, because as Eric says, if you're just adding crappy surveys to crappy surveys, you don't really get very far. So this is really, at this point, kind of the state of the art as to what's going on. It's a bit sad, perhaps, that here we are, but this is the reality of the situation. And we're now trying to wrap this project up. It's sort of been something that none of us get paid to do, and we're kind of gentlemen scientists when it comes to this. So we pick it up on occasion and put it down. But you will be able to come back and talk to you more about this, maybe even in a few weeks before the class is out. Yeah, Michelle. So Michelle's point in the chat, she's saying that we don't really see that bias as much in the off diagonals, right? It really turns out to be that it's more about the strength of density dependence. And remember how Eli was saying that if you ignore this observation error, then you're going to bias these things sort of down. All of these would be biased lower. That means it's sort of stronger density dependence, and you think that's to be the case. But in a situation where, you know, you can imagine you're at some point in time and you don't really know if the observation is here or it's here or it's here, that's a really hard thing for these models to figure out. If these two errors are roughly similar, independent of their magnitude, you can actually still do a pretty good job, especially if you have replicate samples. But in situations where the sampling error, it gets larger than that, well, I should say variance. So this is written for much more of a general audience. That's why I'm using these terms, sampling error and environmental noise. But you could really just think about this as the standard deviation or the variance. As soon as that ratio flips, this gets much harder to do. And honestly, this is somewhat indicative of the work that Kevin and Eli published several years ago. But having done it in this case, so the flip side of this is we have some ability to say how precise you need to be in your prior information in order to actually observe what's going on. And this is, again, it's a totally generic food chain. There was nothing in particular about the way it was set up. So certainly there's going to be some situations where these would still work very well. You know, if you're in a situation, if you're not counting plankton in the ocean, you have a much better chance of figuring out, you know, if you work on trees that don't move, or, you know, like Amelia works on seabirds that nest in cavities, and she can basically walk up to nests and, you know, count how many things are in there, that sort of thing. It's pretty low observation area in those sort of situations, right? They're pretty hard. I just had a committee meeting with a student yesterday who's working on belugas and narwhals And in a classification sense, she had a couple of really bizarre things. And I called out her advisor, Kristen Lydra, who's a colleague of mine. I said, is there any chance that Kristen misidentified these in the field? You know, kind of haha. And I only said that mostly because I figured it was a trans. In the end, the bottom line is no. I mean, the belugas are bright white. You know, narwhals have this crazy tooth sticking out of them, and Kristen's been doing this for 20 years. So it's a, you know, I mean, in those situations, the observation error is really pretty low. But this is, you know, in and of itself, this has been a pretty strong wake-up call for us. Both because if you wrote these models out just the way we've been doing it in class, and you set up a piece of software to solve it that way, the software in and of itself will struggle in many cases. So there are a bunch of little tricks that you have to do behind the scenes. And if you don't know that those tricks exist, you could rapidly fall into these same traps that we sort of fell into and were able to get ourselves out of. So I think I'll stop there in the interest of time, and happy to entertain any questions that people have.
So Mark, I had a funny interaction with Tony Ives years ago, who I know personally because he was a postdoc in, or he was associated with the my PhD lab when I was a grad student. So I saw him a lot. Anyhow, so years later, when we had started working on this and started working on models with sampling error, and we were struggling with estimating the B matrix, and this is separate from Mark's and Eric and Steve's study here. This was a different study, and I talked with Tony. I said, so Tony, you know, we're trying to extend the methods you wrote about in the paper, you know, but we're working with data that's a lot noisier. So, like, what advice do you have for us for working with data that has a lot of sampling error? He's like, oh, I just don't do that. He said that's hard. I solved that problem by only working with data that has low sampling error.
Yeah. Yeah, so right, so Eric has just typed something in here in the chat, and it's like I said, it's true where, you know, a lot of these models that we're using, a lot of them came out of like econometrics and finance and those sort of things. And like I joked about before, money just doesn't go missing, right? I mean, banks have a pretty good idea of how much money they have and that sort of thing. You know, traders know how much money they have, but yeah, if you want to count fish in the ocean or plankton in a lake, it's a much different game for sure. So congratulations everyone for sticking it out.
Yeah. But, you know, I think that, Mark, when I look at this result here, I think, to me, this holds promise, because this says, well, if we could put a decent prior on those diagonal elements of the B, that seems like that's really where the big problems may be. I mean, okay, this is one study, this is a 4x4. But if that were to hold out, like the problems really with the diagonal matrix, that you know, if we could figure out how to put a strong prior on the self interaction, and that seems to me like that's one of the easier things to try to get at is the self interaction.
Yeah, for sure. I mean, like plankton, honestly, if you want to, you know, a lot of work has been done on this because Tony and Brian Dennis and Steve Carpenter, the people that were really the bright minds behind this, had direct access to plankton data. They were, you know, working on these systems. But the truth of the matter is you actually do keep plankton in the lab. It works pretty well. You can keep, you know, big clonal cultures and have those going for a long time. So actually trying to estimate some of this stuff in a lab situation would be reasonably straightforward in many ways. You probably get an idea, what is that strength of density dependence? You know, just count your Daphne over time, perturb the system every once in a while, you know, see how it responds, and then you'd actually get some estimates out of there. So yeah, and as much as any, to Eli's point, this may have not solved the problem, but at the same time, it helps us identify avenues for future research. Like, where if you were going to spend a bunch of time and energy trying to improve this, yeah, trying to tighten up your prior information on that strength of density dependence would probably tell you something. Yeah, so I'll stop sharing there and